Welcome to the Power Electronics class. Myself B. Veernarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We are in third unit, AC to AC regulators and cycloconverters. Here the unit outcomes. At the end of this unit, students will be able to analyze the operation of single phase AC voltage controllers, and unit outcome 2, you are going to analyze the operation of cycloconverters, and here these are the contents present in the third unit: single phase AC voltage controllers and cycloconverters. Coming to this today's topic, single phase cycloconverters. At this end of this class, student will be able to explain the operation of single phase step-down cycloconverter with R load, and explain the operation of single phase cycloconverter with RL load, both in continuous conduction mode and discontinuous conduction mode. In the previous class, we completed the single phase step-up cycloconverter with R load. So here, cycloconverters are nothing but the frequency changers which are used to convert power at one frequency to power at variable frequency. Depends upon the circuit configuration. The cycloconverters are mainly classified into two types: midpoint type cycloconverters and bridge type cycloconverters. And depends on the output frequency, the cycloconverters are mainly classified into two types: either step-up cycloconverter or step-down cycloconverter. If you go through the step-up cycloconverter, the output frequency is always greater than the source frequency. And if you go through the step-down cycloconverter, always the output frequency is lower than the source frequency. From the construction point of view, there is no difference between step-up cycloconverter and step-down cycloconverter. The same midpoint type cycloconverter can be used either as step-up cycloconverter or step-down cycloconverter. And same bridge type cycloconverter can be used as either step-up cycloconverter and step-down cycloconverter. So here we discuss single phase midpoint type step-down cycloconverter with R load. So here the circuit representation of midpoint type. Yes. So coming to the circuit diagram, this is the representation of single phase midpoint type step up or step down cycloconverter. Depends upon the circuit operation or depends upon the controlling of these switches, this midpoint type converter can be operated either step up cycloconverter or step down cycloconverter. Here I just want to operate this midpoint type converter like step down cycloconverter. So here the circuit consisting one isolation transformer whose secondary winding is provided with the center tapping, and it consisting 4 ideal switches which are numbered as P1, N1, P2, N2, and the load is connected between center tapping of the secondary winding of the transformer to this point like this. You can take some P and O, and this consider this is terminal A and this is terminal B and this is C and D. And coming to the operation, I just want to operate this midpoint type converter like step down cycloconverter, and here I want to collect the output voltage which has the frequency F0 is equals to 1 by 2 Fs. Here I just want to collect the frequency which is half of the source voltage, which is half of the supply frequency. So coming to this operation, so here I want to collect F0 is equal to 1 by 2 Fs. What is that meaning here? Previously we discussed step up cycloconverter. In step up cycloconverter, if you take F0 is equal to 4 Fs, what is that meaning? F0 is equal to 4 Fs means the output frequency is 4 times to the source frequency. That means for completion of one full cycle of the source, you are going to generate the four cycles in the output side. Then you are able to collect F0 is equal to 4 Fs. Corresponding that, we are providing the switches. Corresponding that, we provide the gate pulses to the P1, N1, P2, N2. So here I just want to collect F0 is equal to 1 by 2 Fs, which simply reverse. That means for the completion of the 2 full cycles in the source, you are able to collect 1 complete cycle. 1 complete cycle means for this first cycle, you are able to collect only positive output voltage, and after that you are getting the negative output voltage. If you maintain like this, then the output frequency is 1 by 2 times of the source frequency. So how you collect this type of output voltage? How you trigger the thyristors present in the midpoint type converter? So coming to this operation during the positive half cycle, what happens here? Terminal A is positive and B is negative. So corresponding that P1, N2 are in forward bias, P2, N1 are in reverse bias. During the positive half cycle of the supply, here terminal A is positive and B is negative. Corresponding that P1, N2 are in forward bias and P2, N1 are in reverse bias. So here I am taking alpha is equal to 0. At omega t is equal to 0, we provide the gate pulse to the P1. Then P1 comes to the on state and the output current flows through the circuit through A plus, P1, C, P, R, O minus, and in this way the current will be flow through the circuit. Then the upper half of the source voltage VA0 is transmitted to the load, and the output voltage simply follows the VA0. Then what is the output voltage here? From 0 to pi, we have the output voltage due to the conduction of P1. Then this positive portion is available across the load due to the conduction of P1. Next, from pi to 2 pi, we have the negative half cycle of the source voltage. During that negative half cycle, what happens here? Terminal A is negative and B is positive. If terminal A is negative and B is positive, corresponding that N1 and P2 are in forward bias. So, during this negative half cycle of the supply, here P2 N1 are in forward bias and P1 N2 are in reverse bias. But I want to collect the positive output voltage here. So, if you want to collect the positive output voltage, you should trigger the P2. So, if P2 is in the on state, then the current flow through the circuit is this B plus here B plus P2 D P R O minus and B plus. In this way, the current will be flow through the circuit. So here the current is always flows from P to O. Then the output voltage again to have this one. This is the output voltage due to the conduction of P2. You follow simply VB naught. So what is the VB naught here? So here this is VA naught and this is VB naught. So if P2 is in the on state, simply you follows the VB naught, hence we have the output voltage like this. And next, from 2 pi to 3 pi, here you have positive output, positive source voltage, but I want to collect the negative output voltage. So during the positive half cycle of the supply, which are in forward bias, P1 N2 are in forward bias. So out of P1 N2, if you want to collect the negative output voltage, just you provide the gate pulse to the negative group SCR. After P1 N2, which is negative group SCR N2, so you simply provide the gate pulse to the N2. So here from 2 pi to 3 pi, N2 will be in the on state. If N2 is in the on state, then what is the current flow through the circuit? If N2 is in the on state, then the current flow through the circuit is here N2 like this. So here O, R, P, D and N2 and B like this, B minus. So here you can observe here the current flow through the circuit is from O to P, whereas in first two 0 to pi and pi to 2 pi, the current will be flows from P to O, hence why you have positive output current. But from 2 pi to 3 pi, the current will be flows in opposite direction to the previous one. Here the current will be flows in this manner due to the conduction of N2. So you have the output voltage simply follows the this one VB naught. If N2 is on, you follow VB naught and you have the output voltage like this. And similarly from 3 pi to 4 pi, you have the negative source. Due to this negative voltage, P2 N1 are in forward bias and I want to collect the negative output voltage here. So out of P2 N1, which is negative group SCR N1, so simply you provide the gate pulse to the N1 and you have the output voltage like this. So if N1 is in the on state, simply the current will be flows in the same direction. So the direction is given by, if N1 is in the on state, then the current flow through the circuit, see here, R, N1 and like this. So here this is the current flow through the path. So either N1, N2 will be in the on state, then the current will be flows from O to P. If P1 and P2, those are positive group SCRs. If P1 and P2 are in the on state, then the current will be flows from P to O. Depends upon the load requirement. Here I just want to collect F0 is equals to 1 by 2 Fs. Hence why for the first two half cycles, I just want to collect the positive output voltage. So you need to provide the gate pulse to the positive group SCRs. What are the positive group SCRs here? P1 and P2. And after that, I just want to collect the negative output voltage. Hence why we provide the gate pulse to the negative group SCRs depends upon the source. If you have the positive half cycle, corresponding the P1, N2 are in forward bias. If you want to calculate the positive output voltage, you provide the gate pulse to the positive group SCR. And here also we have the positive half cycle, but I want to calculate the negative output voltage. Hence why we provide the gate pulse to the negative group SCR, N2 and N1. In this manner, by periodically you provide the gate pulses to the switches, we are able to collect the output voltage like this. So here this is the simple representation of output voltage waveform for F0 is equals to 1 by 2 Fs. The average of this output voltage waveform can be represented by this one, average output voltage. If you want to draw the output current, here we take purely resistive load na. Hence why the output current is simply in phase with the voltage, and that can be represented like this. Here this one represents the I0. So here this is simply representation of F0 is equals to 1 by 2 Fs. If you go with another exercise, I just want to collect F0 is equals to 1 by 4 Fs, and I want to maintain alpha is equals to 30 degrees. Then the output voltage and the source voltage can be represented. Depends upon the output frequency. Here I just want to collect output frequency is 1 by 4 times of the source frequency. Then you consider 4 complete cycles of the source voltage. 4 complete cycles means this is 1, 2, 3 and 4. 4 complete cycles must be taken. If you go through this output voltage, for completion of these 4 complete cycles of the source voltage, you are able to collect single cycle. Single cycle means for first 2 cycles, you are able to collect only positive pulses. And the next 2 cycles, you are able to collect negative pulses. Corresponding that, you need to provide the gate pulses to the SCRs. So here from 0 to pi, during the positive half cycle of the supply. So if the positive half cycle of the supply means here you have P1, N2 are in forward bias. During the negative half cycle, P2, N1 are in forward bias. So 0 to pi, positive half cycle of the source voltage. Corresponding that P1, N2 are in forward bias. And I want to collect the positive output voltage now. So at alpha is equals to 30, simply you provide the gate pulse to the P1. So from alpha to pi, this portion of the source voltage is simply available across the load due to the conduction of P1, which you follow simply VA naught. And this is representation of VB naught. And again, this is one from alpha to pi, output voltage simply follows the VA naught. And from pi to 2 pi, during the negative half cycle of the source, P2, N1 are in forward bias. But I want to collect the positive output voltage. So you need to provide the gate pulse to the positive group SCR. So from pi plus alpha, why? Because we take alpha is equal to 30 degrees now. So from pi plus alpha to 2 pi, you provide the gate pulse to the P2. Then the output voltage simply follows the VB naught. And again 2 pi to 3 pi, we have the positive half cycle corresponding the P1, N2. So at 2 pi plus alpha, we provide the gate pulse to the P1. Similarly 3 pi plus alpha to 4 pi, P2. So in this manner, we are able to collect the positive output voltage in output voltage waveform for F0 is equals to 1 by 4 Fs. And here from this is 3 pi and 4 pi. So from 4 pi to 5 pi, you have the positive source. During the positive half cycle of the source, P1, N2 are in forward bias. But I want to collect the negative output voltage here. Negative output voltage means you need to provide the gate pulse to the negative group SCR. What is the negative group SCR here? N2. So, from 4 pi plus alpha onwards, we are getting the negative output voltage across the load due to the conduction of N2. And again, like this. Here again N1, N2, N1. So in this manner we are able to provide the gate pulses to the switches, and corresponding that we are able to collect the output voltage. So this is simply representation of F0 is equal to 1 by 4 Fs for alpha equal to 30 degrees. If you want to draw the output current waveform, simply here we have purely resistive load na, so the output current is in phase with the voltage. Output current is simply in phase with the voltage. Then you simply draw this current waveform like this, and the average of this one is considered as the mean output voltage or average output voltage of the midpoint type step down cycloconverter with R load. And if you go through the bridge type step down cycloconverter, we already discussed in step up cycloconverter. From the output voltage point of view, there is no difference between midpoint type converter and the bridge type converter. The same output voltage can be observed, but in midpoint type converter at a time single SCR will be in the on state, whereas in bridge type cycloconverter 2 SCRs will be in the on state. 2 SCRs will be in the on state. So during the positive half cycle of the supply, there P1, P2 are in forward bias. So instead of P1, we are getting P1, P2. During the negative half cycle of the supply, P3, P4. Then you are able to collect, instead of P2, P3, P4 will become here. That is the main difference. And operation point of view and the output voltage and output current will be same for both midpoint type cycloconverter and the bridge type cycloconverter. Now we discuss this midpoint type step down cycloconverter with R load. Now we consider bridge type cycloconverter under step down operation with RL load. We will discuss. So the next one is single phase bridge type step down cycloconverter with RL load. Single phase bridge type step down cycloconverter with RL load. So coming to the circuit diagram, RL load, and here you have the source, and the same source is also connected here. Yes, here this is the P type converter which consisting P1, P2, P3, P4. Yes, so here this is P converter, and here it is N converter. And here you have the source. Here I just want to collect for alpha is equals to 45 degrees. I just want to collect F0 is equals to 1 by 3 Fs. And you know, if you have the inductive element in the load side, here R and L, across this you have the output voltage. Depends on the value of inductor, this converter should be able to operate either in continuous conduction mode or discontinuous conduction mode. If you have the low value of the inductor, then the converter operates under discontinuous conduction mode, and if you have the high value of the inductor, the converter operates in continuous conduction mode. First we go through the discontinuous conduction mode. So I am assuming low value of inductor, corresponding that we are able to collect the discontinuous conduction mode. So under discontinuous conduction mode, I just want to collect the output frequency 1 by third of the source frequency, and I want to maintain alpha is equals to 45 degrees. So here the source, here what is the meaning of F0 is equal to 1 by 3? 1 by 3 means for completion of the 3 complete cycles of the source, we are able to collect 1 complete cycle. So you consider the 3 cycles of the source. 1, 2, 3. Here this is the representation of output voltage, and here this is the representation of the output current. So coming to this operation, during the positive half cycle of the supply, here terminal A is positive and B is negative. Here terminal A is positive and B is negative. Corresponding that P1, P2 are in forward bias, P3, P4 are in reverse bias. In the P converter, during the positive half cycle of the supply, here P1, P2 are in forward bias and P3, P4 are in reverse bias during the positive half cycle of the supply. Coming to the N converter, A is positive now, then N1, N2. Here during the positive half cycle, in the N converter, N1, N2 are in forward bias and N3, N4 are in reverse bias. So during the positive half cycle of the supply, here P1, P2 are in forward bias and N1, N2 are in forward bias. From the P converter, P1, P2, and from the N converter, N1, N2 are in forward bias. If you want to collect the positive output voltage, then you need to provide the gate pulse to the P converter SCRs. If you want to collect the negative output voltage, then you need to provide the gate pulse to the N converter SCRs. Similarly, during the negative half cycle of the source, here P3, P4 are in forward bias and N3, N4 are in forward bias. If you have the source as negative half cycle and if you want to collect the positive output voltage, you need to provide the gate pulse to the P converter SCRs, which are P3, P4. If you want to collect the negative output voltage, then you need to provide the gate pulse to N3, N4. Simple. So here 1 by 3 Fs, that means 1.5. Up to this, we have the positive pulses in the output voltage. Next 1 half, second half and next 3 half cycles, you need to maintain the negative output voltage. Corresponding that, you provide the gate pulses to the particular SCRs. So see here, for alpha is equal to 45 degrees, during the positive half cycle, P1, P2 and N1, N2 are in forward bias. And here, alpha is equals to 45 degrees. I just want to provide the gate pulse to P1, P2. So if P1, P2 is in the on state, the output voltage simply follows the PAB. And the current will be flows through the circuit is given by like this. Here P1, P2 are in the on state from alpha to pi. At omega t is equal to pi, even though the output voltage is 0, the output current cannot be 0. Due to that, why? Because from alpha to pi, there was some energy must be stored in the inductor. And the current flow through the circuit is given by A plus P1 R L P2 B minus and the source. So during that, there was some energy must be stored in the inductor. So the energy must be stored in the inductor is completely discharges before pi plus alpha. If the energy stored in the inductor is completely discharges before pi plus alpha, then we are getting the discontinuous conduction mode. If the energy stored in the inductor is discharges up to pi plus alpha, then you are getting the continuous conduction mode. Here first we go through the discontinuous conduction mode. Hence why before pi plus alpha, the energy stored in the inductor is discharges. So here this is beta, which is called extinction angle. That extinction angle is defined as the conduction period of the SCRs is extended due to the presence of the inductor. That conduction period is extended up to which instant? Up to the energy stored in the inductor is completely discharges. So that pi to beta also P1, P2 are in the on state. P1, P2 are in the on state. And from pi to pi plus alpha, all are in off state, and hence why there is no current flow through the circuit. And again, from pi plus alpha to 2 pi, you have negative half cycle of the source. Due to the negative half cycle, what happens? P3, P4 comes to the forward bias, N3, N4 are in forward bias. But I want to collect the positive output voltage. So if you want to collect the positive output voltage during the negative half cycle of the source, which devices comes to the on state? P3, P4. P3, P4. So you need to provide the gate pulse to the P3, P4. Hence why output voltage will be like this. And output current will be rising in nature, and this is the output voltage. But at 2 pi, even though output voltage is 0, the output current cannot be 0. Hence why the conduction portion of that P3, P4 are extends up to this instant. So here this is the on state of P3, P4. Hence we are getting the negative pulse. Similarly here also. And again same, again current charging, discharging. Again here P1, P2. Like this. and this is important. Here pi, 2 pi, 3 pi, 4 pi. So see here, from 3 pi to 4 pi, you have the negative voltage, negative source voltage. Due to that P3, P4, N3, N4 are in forward bias. But I want to collect the negative output voltage. So negative output voltage means you need to provide the gate pulse to N3, N4. And hence why this is negatively charged and negatively discharged, and some small portion of the positive. And again like this. So here also negatively charged, discharge, and negatively charged. So here N3, N4, and here N1, N2, and again N3, N4. So this is the output voltage and output current waveforms for F0 is equal to 1 by 3 Fs under discontinuous conduction mode. And last one, for alpha is equals to same 45 degrees and F0 is equals to 1 by 4 Fs, and assume high value of inductor. Then you are able to collect the continuous conduction mode. So under this continuous conduction mode, how the voltage and current waveform should be collected, we will discuss. Simply one, 2, 3, 4. This is V0 and this is I0. So here I am going with continuous conduction mode. So if you go through the continuous conduction mode and F0 is equal to 1 by 4, that means for completion of 4 cycles of the source, we are able to collect the one complete cycle. Hence why for the first 2 cycles we have the positive voltage and next 2 half cycles negative voltage. Corresponding that you need to provide the gate pulses. During the positive half cycle, what we are having the forward bias P1, P2, N1, N2. During the negative half cycle, P3, P4, N3, N4. So see here, from 0 to pi, you have the positive half cycle of the source, P1, P2, N1, N2. I want to collect the positive output voltage. So simply from alpha to pi, you need to provide the gate pulse to P1, P2. And the current will be charging. And pi to pi plus alpha discharge. Hence why you have the negative portion due to the conduction of P1, P2. And again P3, P4. Current again charging, discharging. And again P1, P2. Current charging, discharging. And again P3, P4. Charging, discharging. So 1, 2, 3, 4. First 2 cycles you have the positive pulses. Next, here you have the positive source voltage. Due to that P3, P4, N3, N4 are in the on state. But I want to collect the negative output voltage. Then what happens here? You need to provide the gate pulse to N3, N4, and again N1, N2, N3, N4, N1, N2. So here also, sorry, like this. This is due to the conduction of N1, N2 and current like this. So here current negatively charge, discharge, charge, discharge, charge, discharge, like this. Continuous conduction mode means you have the continuous negative pulses. First 4 positive pulses and the next 4 negative pulses, and this is the representation of output voltage and output current waveform for continuous conduction mode under bridge type step-down cycloconverter. So at the end of this lecture, student will be able to explain the operation of step-down cycloconverter with R load, and you are going to explain the operation of step-down cycloconverter with R and RL load. Okay, thank you.